you for the invitation, and I am truly very sad not to be there, but thank you for the opportunity to still present here from Colorado. So I've gotten to watch most of the talks this week, even though I'm remote, and they've been fantastic. I must admit, my talk feels pretty simplistic, but bear with me, because by the end, I hope to have some fodder for discussion, at least on topics that I've been thinking a lot about lately. So just to give you some background, I am very much a domain scientist. I'm a climate scientist here at Colorado State University. And so I'm really coming at it from the domain side, but thinking about how to apply these tools to climate science problems. All right, and please feel free to interrupt. I know it's a little bit more awkward when I'm not there in person, but try anyway. Okay, so we've already heard the word chaos a few times, and everybody in the room knows what it is, but I just wanted to get you in this mindset, this concept that small differences in initial positions can lead to enormous differences in the final phenomena. And the concept that prediction potentially of our Earth system or the climate system becomes impossible. And Maria yesterday, one of the closing talks, talked a little bit about this idea that maybe we can't make forecasts all the time, and there may be certain states of the system that are more predictable than others. And that's really what I want to focus my entire talk on today. It's really a framing of the problem. So again, the Earth system is exceedingly complex and often chaotic. And so prediction's really, really hard. And I am going to try and be a little provocative and say, instead of we cannot expect, maybe we can't make perfect predictions all of the time. It's just not going to ever be possible. And you can argue with me on that, maybe to make it interesting. So this is where this concept of forecasts of opportunity, but I'm going to start to use a slightly different phrase, state-dependent predictability, because I want to be very clear, this does not require that you're forecasting weather or a climate variable. It could be that you are making predictions of something completely different that has nothing to do with time. But the whole concept of state-dependent predictability, or again, forecasts of opportunity as it's called in the weather world, is that certain conditions lead to more predictable behavior than others. And so part of being, an atmospheric scientist or a climate scientist is thinking that beyond the weather timescale, we have to look for specific states of the Earth system, i.e. these opportunities, that lead to enhanced predictable behavior. Otherwise, we're doomed, if you will. And a phenomenon that many of you may be familiar with is the concept of the El Nino Southern Oscillation, which is a climate mode of variability that is directly linked to variations in tropical Pacific sea surface temperatures. And the idea is we know in a broad average sense that when the Pacific Ocean looks a certain way, we may expect precipitation differences across the globe. Either some regions will be wet, others will be dry. And if this mode changes sign, then maybe everything gets a little bit flipped. Now, I will point out, this is the average, not how it actually works out, but there's already this concept that we have that certain states of the climate system may lead to behavior or anomalies elsewhere on the globe that we can use to make more accurate predictions. So, one of the big challenges then is how do we identify these forecasts of opportunity? So when do they occur? Why? So physically in terms of, physics and mechanisms, where is it coming from? And then finally, how do we intelligently leverage these opportunities for our predictions of, again, weather, climate, etc. I will point out, you may be familiar with ENSO, or the El Nino Southern Oscillation, but another one that, again, Maria mentioned a few times yesterday is the idea of the Madden-Julian Oscillation, which operates on monthly or weekly time scales. And this phenomena is dry and wet regions that propagate eastward within the tropics. You can see these brown blobs and these green blobs moving to the east. And what's important is with this phenomena is when we have dry and wet regions, they can excite waves that propagate into the mid-latitudes and lead to changes in where the storms go, where it rains, where it's dry, etc. So in addition to all this, we have these climate phenomena that can influence weather across the globe. But again, only when in this case, this MJO behavior is active. So we need to identify these opportunities when this is happening, and then we may have more predictable behavior elsewhere. So how are we using machine learning to think through some of these ideas? I'm going to jump right into some applications, and then I'm going to back up into a little bit more theory. So Kirsten Mayer here in my group is thinking about subseasonal weather prediction. Again, the subseasonal timescale Maria already went into yesterday. And thinking about how tropical information, so these maps of tropical convection, can be fed into a neural network to try and predict what's going to happen to the atmosphere, in this case, 3 weeks later over the North Atlantic. So far away up in the North Atlantic, you know, somewhere near Greenland, if you will. So she trains a neural network to ingest these maps and make a prediction. And I can talk about the details of how we do that. But one of the big points here is we can then go in, since this is the way she does it is a classification problem, we can use these output, if you will, likelihoods or probabilities and make a plot that looks something like this, where we plot the most confident or the percent most confident predictions on the x-axis, which we're using as the from the output of this neural network versus the actual accuracy that we see in those samples. And again, if you were to train on all data and then test on all data, you would have the far left values. So you would, you know, she's predicting whether the circulation is positive or negative. So this is a 50-50 chance here. So that's drawn here at 50-50. And her neural network's only doing about 55% accuracy. So it's only a little bit better than random chance. So you might think, oh, this is sort of a failure. This isn't very helpful or interesting. But if you start to look at how these predictions actually work and how the network is, what the network is doing with the most confident predictions, we see that when we get into this right-hand side where the network's most confident, our accuracy is much higher. That is, the network is identifying certain patterns within the system that lead to more predictable behavior. And indeed, it is more accurate when it makes its predictions. And so in our group, we're really spending time thinking about, in this case, Kirsten really focuses on the top 10% confident predictions, but you know, you could look at the top 30% most confident predictions, etc. Now, with this in mind, we then use explainable AI often to understand the physics of where this predictability is coming from. You know, what in the tropics is leading to these highly confident and or more accurate predictions. And in that way, we use explainable AI to go back through the network and look and to help us identify regions in the tropics that were most useful for the network to make its accurate and confident prediction. And again, I'm not going to be spending most of my talk on this topic, but I'm happy to talk about it during questions. So Kirsten can do this and then go and make maps in the tropics. So this is that tropical box that really highlights the regions that the network identified as most important for its confident and accurate predictions. And then as domain scientists, we can go through and try to understand why these particular regions were so highly relevant for the predictions. Now, this is sort of in a typical weather setup. I want to show another setup thinking about forecast errors. Again, I think it made sense that I'm after Maria here. She also talked about yesterday about predicting errors in the models instead of predicting the actual field itself. So this is something Jack Cahill here is doing, but the same concept. He is inputting into a network tropical maps again, but then he's trying to predict whether our state-of-the-art NOAA weather model called the UFS, so this is a dynamical, so a physics-based model, whether it's going to have a big error in 10 to 14 days. So in 2 weeks' time, is that UFS forecast going to be really off or wrong and positive? So a large positive error, will there be a large negative error, or will there be a near zero error? So given what today looks like, what does the network think the UFS is going to do in terms of its error in the next 14 days? Again, in this case, this is classification. So a random chance would be a third, a third, a third. That's drawn here in this dashed line. And if you look at all of his testing samples, you'll see again, the network doesn't seem to do much better than random chance. It's really around 40% accuracy in predicting what that error will be. However, if you once again look at the far right, you look at the maybe top 50% most confident samples, again, it appears the network has identified particular states of the system that lead to more predictable errors in the UFS model. So this doesn't just need to be used for weather prediction itself. Sorry, just again pointing out, these are regions that we have much higher accuracy and the network has predicted. It's more confident about what its prediction is, and indeed it's more accurate. Okay, so I've just showed that for regression problems. And so anyone doing a classification problem already through that softmax output has some form of, if you will, hand-wavy likelihood or confidence from the network, and then you can use that to filter out when's the network confident or when is it less confident, and see if you have more accurate predictions when it is more confident. But what about regression problems? And this is what my group has really been thinking about. Again, as domain scientists, we spend a lot of time doing regression, not classification. A lot of what we do is in terms of actual, a list of many numbers in a row, and how can we still use the same idea of forecast of opportunity or state-dependent predictability? So I want to take you back to Laura gave a talk, I think now a few days ago, thinking about predicting uncertainty for these regression tasks. And that's what I want to talk about briefly here. For the computer scientists in the room, my understanding is this is pretty vanilla, if you will, everybody knows this, but from a domain scientist perspective, this was news to me, and it's really been a game changer actually in what we've been doing. So rather than just have our network take some input and predict a single value, we're going to have our network take some input and predict 4 values. So in this case, this is my new favorite distribution. This is called, here we go, the hyperbolic sine arc sine normal distribution, or the family of distributions. And why I really like this set of distributions, it takes 4 parameters, but one of those sets of distributions is a standard normal, or just a normal distribution. So if your data should be, if your conditional distribution of your prediction really should be Gaussian, this will find that. And I like that because oftentimes it is Gaussian. But once in a while, and I'll show you some examples, it's not Gaussian, and it's instead skewed. And this distribution can take care of that in a knowledgeable way. So what we're going to do is we're going to train our network. So again, instead of predicting a single value, to predict 3 or 4 of these parameters to predict some conditional distribution of our output given our input. And I'll show you what I mean by that. So imagine we have some data set. This is very, very simple. We have some X data that goes into our network, and we want the network to predict Y. So again, by eye, you could draw a line of the best prediction, but this is just a toy example. A few things to note about this data. It's a heteroscedastic. It also has changing skewness in Y depending on where you are in X. And the idea is we want a network to go in and actually be able to predict this range of uncertainty of the Y if we give it a particular X value. And in using this simple framework of just having it predict this, these 4 parameters of this distribution, we end up with something like this. So this is the network's prediction, and just pointing in on an example. So when we input an X of about 0.7, the network actually outputs that full blue skewed distribution. And you can see those vertical lines actually give you the 80% data on, or the 80% confidence bounds of that predicted distribution, showing that the network was able to learn not just the general pattern, that nonlinear pattern of Y, but also its uncertainties as you move along in the X direction. All right, how do we do this? I'll talk briefly just to point out the way we do this is we train it with our loss function. That's just minus log P. And what I mean by that is the network predicts some distribution, again, drawn here in blue, and the loss function is defined by evaluating that PDF at the true value Y, because again, we wanted to ultimately predict some Y value. So you evaluate it, some true value Y, the P is just the value of that PDF at Y, and that is your loss. It just goes into minus log and that of that P value. And it turns out this is directly related to maximum log likelihood estimation, or maximum likelihood estimation in statistics. So you can imagine how is this actually working, doing this prediction? Well, it works by, if your network's overconfident, it's going to predict a distribution that's really skinny. And so when you evaluate it at the truth, that p-value would be quite small. Alternatively, which is bad. Alternatively, if your network's way underconfident, it's going to predict a really broad distribution. So when you evaluate it at that p, at that y value, once again, it's quite small. So it's really the network trying to find the right distribution so it can really make the p, if you will, as big as possible. So I'm getting into what I mean by I don't know, don't worry, but here, ultimately, why were we doing this? We needed some way to get some uncertainty of the network in order to then start to ask questions about, is the network more accurate when it's more confident, and how can we use that in this sense of state-dependent predictability? But just to show you briefly how this is working, this is new work that we've been doing, where we're actually working to try to create a methodology for operational hurricane forecasts. So for example, on the top, the true hurricane forecast 72 hours later is drawn in blue. So this is the intensity of that hurricane on September 14th. And the consensus, that's another way of saying what the National Hurricane Center really uses, one of their best predictors of the intensity, is shown in yellow. And we've trained our neural network to predict this conditional distribution, and that's drawn in pink. So the network says there's pretty much no way the consensus is correct. And it gives a distribution for what it thinks the true intensity is, as well as, you know, an actual prediction, in this case by the median. And I will point out we're also doing this for track forecasts as well, which is a little bit trickier. But ultimately, the whole goal of this is not just to get a distribution, but to actually use it to then identify, are there forecasts of opportunity? Are there times when the network is more confident than others? And why is that physically there? So Emily Gordon in my group has been thinking about this in terms of decadal prediction. So thinking about what's going to happen in 1 to 5 years in advance. And again, this is the same type of plot I've shown you a few times now. So she ingests ocean heat content into, again, a neural network and tries to predict what the sea surface temperatures over the North Atlantic will be in 1 to 5 years. When she does that, she then she trains the network to predict both a mu and a sigma, so in this case a Gaussian, and then filters those predictions based on sigma, based on that uncertainty of the network. And that's what's shown here on the X. So again, 100% most confident is all of the testing samples. So this is what you would typically think of as her predicting everything. And then as you move to the right, this is the more and more confident samples. Just to be, sorry to be confusing, but the y-axis here is actually error now, mean absolute error. So it's better if you're lower. So if you're a smaller number. And what we see is a great example, I think, of the state-dependent predictability, where that error slowly goes down as you get the more confident samples, but then around 30% most confident samples, there's a sudden drop-off, suggesting again that there's something physical in the climate system that the network is identifying to lead it to be more confident and reduce its error significantly. Okay, so this leads to the next idea, which is we're doing all of this sort of offline, or after we train a network, then we use the certainty to filter out our predictions and focus on the most confident. And this leads into some more sort of theoretical or algorithm work that we worked on this past year that we call controlled abstention networks. And the idea here is we have a new loss function called the abstention loss. And by the way, by abstentions, I mean saying I don't know, or saying pass, I don't have a vote, right? Like I abstain. So the idea is, can we train a network to identify the more confident samples while training and abstain on the less confident samples? So the idea is to have it preferentially learn the more confident samples better. And this, again, is coming from the concept that there just may be some samples or some predictions that are just impossible. And why are we setting our network up to get confused by those when if we really wanted to focus on the ones that actually have a chance of being successful? So there are some, I want to point out that our work has been heavily influenced by some work done in computer science in the last year. And I will also point out that we've done this for both classes. We have a paper on classification and a paper for regression, but I'm going to briefly talk about that for regression now. Now, to compare this abstention network process, we want to compare it to what would we have done without it. And that's really this baseline approach that I just told you about, that I just showed you. The idea is that after we've trained a model, for each sample, we predict some probability distribution. And after many samples, we have many of these predicted conditional distributions. You know, some are more certain, some are less certain. Doesn't mean they're right, but this is according to the network. And then we can filter out the least certain and really focus on the most certain as those opportunities potentially for successful forecasts. And this is really that baseline approach that we want to compare to. And the question is, do we do better when we allow the network to learn preferentially on the more certain samples rather than just after the fact? So let's talk about abstention during training. I'm not going to go into all the details here, but again, happy to talk about it later. But the whole idea now is our loss function is no longer minus log p, although you can see that hiding here in equation 4. Instead, it's that we have a minus log p plus a few extra terms, which end up giving us weighting for how much we want to abstain or have the network focus on the more or less confident samples. And so this particular loss function has an equivalent in classification problems as well. But ultimately, this allows us to control how often our network abstains or says, I don't know, while it's training. So just as an example, this is, while training our network, this is epoch on the x-axis, and on the y-axis is how often the network abstains. And as a user, I went in and set it at 70%. And you can see the network try and figure out how to say, I don't know, about 70% of the time. You can also have the network tell you how often to say, I don't know, and then I can talk about that later. But here's the whole concept again of this state-dependent predictability. And this was the simple example I came up with, and I said, I want a network that can do this. So imagine again, this is your data set. So again, X and Y data, so really easy to visualize. Imagine that 80% of your data falls in some blob of noise, and only 20% of your data actually falls along some pretty straight line. If you were to go in and do a best fit line through this data, it would perform poorly on everything. So, everybody loses, if you will. Now, as a human, I can look at this data and say, okay, the blob is noise and really hard to predict, but I'm going to really focus on that 20%. But we can do that because this is sort of obvious in this example. And in the climate system, our data is really complex and hard to visualize, and we rarely can have such a nice visualization. So this was the whole idea of this abstention network, because we want it to learn the line and also learn to ignore the blob. And so indeed, we can actually, that's what happens, is the abstention network learns to abstain on 80% of the time, and actually really only focus on 20% of the data. And it learns that line very, very well, and also learns to ignore the blob, which is what we wanted. And now you might say, okay, but what about the baseline method? Couldn't you have just trained a neural network and then thrown out the least confident samples? Wouldn't you have done as well? Well, good question. So this is how we plot that. So the percent coverage again is on the x-axis. So how often what percent of the data it makes a prediction on, and the mean absolute error is here on the y. The solid purple line is that baseline method that I've been showing you thus far in this talk. And the whole point here is that indeed the abstention network does better than that baseline because it was allowed to learn preferentially on the more confident samples. Now, this is a very silly, simple example, of course. So I will quickly just go through and explain that, yes, we have applied this to more complex data sets, and the same results are true. Mainly, a postdoc in my group here with Dr. Emma Ebert-Uphoff, Dr. Antonios Mamalakis, has made a synthetic climate data set that's been great for testing some of these ideas in a more realistic setting, but without yet going to real data. So in essence, what he's done is he's created a data set where the X's are multivariate maps that behave something like sea surface temperature. So they have similar variability patterns. And ultimately there is a Y, a single value that's a nonlinear sum of this map associated. So these are, if you will, are the labels of each of these maps. And so ultimately one can train a network to take in or ingest a map that looks something like sea surface temperatures and predict this Y value. But instead of predicting Y for this example, I'm going to predict this conditional distribution. Again, I'm going to use a Gaussian because I know that it will be a Gaussian because we made the data, right? So we're going to predict this mu and the sigma, but we're going to go in and be a little bit sneaky. We're going to go in and we're going to look at every map, and we're going to say only when the tropical Pacific is a big positive value, that is, in essence, when we have synthetic El Niños, we are going to keep the Y value untouched. But all other cases, like in La Niñas or when it's about 0, we're going to shuffle the labels so they're completely meaningless. That is, we've hard-coded in the fact that there are a lot of samples with no learnable relationship with its label. That is, we need the network to identify certain situations, in this case, El Niños, that lead to predictable behavior, while all the other samples are, if you will, noise. So we've done this with this abstention network, and again, compared it to the baseline. Again, the baseline is just training the network like normal, and then filtering out the most confident samples and only focusing on those. So again, error of the network is shown on the y-axis, so lower is better. And once again, we see that the purple line is that baseline approach, so the error goes down as you filter out the the less confident samples. But the big point again here is that the dots, which are the abstention network, perform better than this baseline approach. Again, highlighting that the network is being allowed through this loss function to learn the more confident samples better. And I will point out we've applied this now to more than just that one example. This can be used to use as a data cleaner to identify corrupted inputs. It can be used for, again, forecast of opportunity if your labels are somehow shuffled or you have certain corrupted labels or structured noise. Okay, so that is the approach, but I want to end here. I'm a little bit early, but I want to talk through why I thought to tell you about this particular audience. So it's really all comes back to this idea of state-dependent predictability. And I think it's incredibly important that when we talk about predicting and understanding and modeling and analyzing the climate system, that we don't forget that a lot of these problems are really, really hard or near impossible in terms of these prediction problems, but that sometimes we have these windows when we are able to make better predictions. So I'll go through a few examples here. So my first point is that I think this is more than just uncertainty quantification. Sometimes I show this and people say, oh yeah, you just want uncertainty. Yes, uncertainty is necessary. We need the network's confidence in its prediction in order to do this. But I think it's more than just uncertainty quantification. It's more than just some post-processing problem. I really think that it's worthwhile for anyone working on AI for climate to really consider taking this mindset of state-dependent predictability, because you might actually set your problems up differently. You know, why have you chosen to try to predict everything all the time? Why are you trying to minimize the error over all time rather than just specific times? The answer could be because it's easier or it's hard to identify when you should be focusing, and that it makes sense. Another one is just the general concept that impossible predictions may be hampering learning of predictable behavior. Again, I think this is different than some of the more classical examples of AI, where it's, tell me if there's a dog or a cat or a spoon in this image. Ultimately, the concept is that there is a truth. There is a dog or a cat or a spoon in that image. But I think when you get into a climate system, it gets a lot fuzzier. And we're not really sure if we should be able to predict what's going to happen. So this could be predicting climate variables in terms of weather forecasting or climate forecasting, but could also be thinking about forecasting particular errors to try to understand your particular model. And another thought is, could it be helpful? Could this type of thinking be helpful in sort of separating out your data set into those that were easier to predict and having a network for that, and then having the model kick out the harder to predict samples to be maybe trained or learned in a different with a different architecture. Number 3, and this is something I've been talking to Mike Pritchard about, is I wonder if this type of idea in certain contexts, when it makes sense, could be helpful for hybrid approaches to climate model parameterizations. Maybe this is done already, but this is something that Mike and I have been discussing, is could we use uncertainty measures or abstention to kick predictions to the machine learning parameterization or physics-based parameterization in real time? So that is, if a sample is identified by machine learning as being an I don't know, then it kicks it to the more time costly physics-based parameterization. Could this also be helpful for identifying out of sample climate change? Again, with parameterizations, maybe if the network identifies that, hey, this isn't a sample I really know what to do with because the world is slightly warmer, I'm going to kick it to the physics-based parameterization where the fact that the temperatures are rising is sort of in the equations already. And finally, my 4th one here, I think, you can correct me, I think the utility of this whole concept revolves around the fact that we don't have a lot of data. And correct me if I'm wrong, but my thinking is if we had an infinite amount of data, the network should be able to learn all the predictable behavior within it and ignore or not learn any of the noise. But unfortunately, that's not the situation. So I do think this mindset is pretty important, especially when we have small sample sizes, because our networks or our machine learning algorithms potentially will try and put a lot of energy into learning relationships that really are not learnable. So with that, I have some reference links if anybody's interested. So I'll just put that up so someone can pause the video, and I will take questions.
Thanks, Libby. That was really thought-provoking. I'll kick it off with some of my own questions. So first off, it's interesting that the wheel is being rediscovered in different domains. You may want to check, Joachim Freund at UC San Diego did learning with abstention a long time ago, although I was just looking for it and I couldn't find it on his webpage. There's also this literature on curriculum learning where you order, it's sort of the opposite. You order the samples in terms of hardness. So you can drill down on getting really hard examples near the boundary first. And then also, this sort of reminded me of active learning, a field where I used to work. And this leads to my question, which is that, so in active learning, you pay for labeled examples. And so you could abstain to ask for a label if you have high certainty. In your case, you're not going to make a prediction if you have high uncertainty. But you do get into the situation in both cases that you could just abstain. And if you don't have enough data, is there a chance you would not be making any predictions at all because your threshold on uncertainty below which you're willing to predict doesn't allow it? So is that like just a hyperparameter that you tuned?
Yeah, so no. So actually we never set a threshold. So I'll back up. Good question. So I will back up and say, I pointed out a computer science PhD out of University of Washington that framed this abstention framing. I will point out, Claire, and again, I don't know this specific paper you're addressing. There have been others that use this concept and that go back for decades. I don't want to say that no one's ever thought of this idea before. I think what we have provided here, I think, is we have done it very, very, very simply. So our goal here was actually for I guess partially in terms of communication. I have found abstention networks that actually require you to reframe your entire architecture. And so one of our focuses here was how do we get it to only require you change the loss function and nothing else. So thus it could be applied at sort of at the end to any architecture. And that's again, piggybacking off of this previous work at University of Washington. So thank you. I don't mean to say that we're the first to say I don't know at all. In terms of your question, so we don't actually set any thresholds. No, that's not a hyperparameter. We actually have framed this in two different ways. One, we actually have it so the network uses what's called a PID controller to attempt to keep the abstention fraction at some user-defined value. So the one thing the user has to choose is how often do you want to abstain? Do you want to abstain 30% of the time? And you set that, and then the network attempts to set its own thresholds to achieve that. Alternatively, you could say, I don't know what percent it should abstain on. And then in that case, it's not so much a threshold, but you try and have we have a setup so the algorithm actually then is more free to determine what it should abstain on. However, with it, finally, it is absolutely possible the network could abstain all the time, but that's pretty rare given that we have this flexibility in how the user can actually use the tool. Does that help? Sort of. That was a little vague.
Fantastic. So we have 2 people lined up here. We have 3 people on Zoom. Why don't we alternate? So unfortunately, if your video is on, I don't see your name, but the woman who is not Laure, could you go with your first question?
Judith.
This might be me. Hi. Thanks so much. Very interesting talk. First to state the obvious, obviously this would be very interesting to do in terms of S2S predictions, because there we have these windows of opportunity, but generally climatology is better. So I'm sure you have thought about this, but that would be a really nice application. The other question I have is, as you know, in weather prediction, subseasonal, and we should do it in longer time scales, but we don't. We use the spread error correlation. So we run an ensemble, and if the ensemble spread is large, we think this is an uncertain forecast, and if it's small, we want this to be a certain forecast. That's what we want for a reliable ensemble prediction system. How does this spread in the ensemble system relate to your confidence? And I'm not using the right word, but you know what I mean.
No, I get you. So great. I'll give you my hand-wavy answer, but my short answer first is, this would require a lot of deep thinking in how this works, because we're not there yet. This is very new. So I think you're bringing up a great question that one could do research on. With that said, we have not taken an ensemble approach, and I'm aware that the community, that's how we often do it, right? We use the ensemble spread. If, the network is taking lots of types of uncertainty, it could be uncertainty in the actual inputs themselves. It could also be in the uncertainty due to the noise or the chaos of the climate system. It could be uncertainty due to that actual relationship, and if we have enough data to identify it. All that's being bottled up and put into this one confidence value. So it's a bit of a mess when you try and split it out into where is this uncertainty coming from. However, if this were working properly, the hope would be that if your ensemble was good, that if you were to run your dynamical forecast model and you got a large ensemble spread, my hope would be that then the network would potentially also identify that as an uncertain sample. I think the benefit of this approach was, how can we do this on data alone? Maybe if we didn't even have the dynamical models. But more importantly, I think the interesting research questions is, how could we couple this with the ensemble approach we already have to leverage both and make even better predictions? And I don't have a good answer for you. And if I was, well, you're not there either. Maybe we should just yell to each other. But yeah, I think this is exactly what I would love to be talking to people about, because I don't know, I haven't thought about it yet. And I think we need to put our heads together.
Great. Now an in-room question from Micah.
Is this on? Excellent. Thanks. That was a great talk. I have two questions that maybe sort of are the same question, but to your design of the training data that was looking at ENSO, I think Antonio's work. There, you sort of go in and decide. Right. You say, okay, I want this signal. This is ENSO, this is what I'm going to be looking for. And to some extent, if at least I'm not aware of knowing exactly what to look for to be able to predict ENSO. So in that sense, do you think taking something, ENSO is a big climate signal. It sticks out like a sore thumb, right? So in that sense, it's probably a good thing to start with. But do you think there's a danger for biasing what you can find by your design of a data set in that sense, because it's such a global interconnected signal?
Oh, okay. So I'll back up here. That ENSO example was, you should think of it as a toy example. That was just proof of concept that it worked on multivariate data, and we thought it would be fun to make it, if you will, look like real data.
Okay.
And so that was me, if you will, playing omnipotent being and going in and setting up this system that was at least complex enough that the climate scientists wouldn't go, psh, this is just 2D data. What are you doing? But that was me playing omnipotent being and then showing that it still beat the baseline. You wouldn't, as if you were to actually use this method on your own data, the expectation is you don't know what those states are, or how big they are, or how global or small they are. So I may not have introduced that correctly. Does that help?
Yeah, I guess my understanding of what you were doing was that it was sort of related to ENSO specifically, and that
was just a toy. We said, how are we going to? What state do we want to be most predictable? I could have made it that Minnesota had temperatures over 2 degrees, and I could have used that to filter out my data. I just used ENSO because it's something that people are familiar with. So there's nothing special. You know about ENSO, and I'm just saying there's nothing special about ENSO for this example. It was just a toy.
I guess this sort of also comes to my second question, which maybe I've also misunderstood how you think about this. But when you were saying that there might not be something sort of specific, and that the climate system might, and to some extent, be too hard in the ways that we've been thinking about it, and sort of trying to apply machine learning and learn about the system, is that because you think or have experience of having the interconnections be hard to sort of crystal out in that sense? Because you seem to be attempting to sort of pick the system apart in a particular way, which you might be right, might be just too hard simply. So I guess in a way I'm saying that the things we're looking for are emergent, and that finding those underlying ground rules is to some extent the holy grail we're looking for. And you seem to suggest that you have to sort of chop up the system to be able to understand the separate bits. And those two ideas sort of seem perhaps complementary, but somewhat sort of different approaches.
Yes, they are different. And I would actually say, you're right, I am chopping it up. That's thus far in my career, my feeling has been, if we're going to make, for example, subseasonal prediction, I think for a long time was dealt with in the way weather people, like the weather forecasters dealt with it, which is looking at the very underlying pieces. And I think we've made a lot of progress because we've started chunking it up into these different pieces. It'd be great if I was wrong. So yes, you hit the nail on the head. This talk was absolutely meant to force people to think about this chopping it up approach. Do I think that am I confident that this is the only way? No. And so the next, 5 years, 10 years of everybody working together, maybe we'll find that this isn't the right way to think about it. But I don't think a lot of people coming in from the outside think about it this way. And so this is meant as a provocative thought exercise. How's that?
Yeah, no, I wasn't meaning to push you in either way.
No, but I mean, great. Yes, I think you've identified two really important ways of thinking, and you're right. I do think at the moment they do feel separate, and I'm wondering maybe if we can make more progress in climate modeling and AI if we try and connect them a bit.
Yeah,
better.
exactly. That was exactly what I was getting at.
Cool.
Okay, great.
I want to give the floor to Laura for a question.
Right. Yeah. Thanks, Libby. That was fantastic as always.
Okay.
So your point 3 here, can you tell us a little bit more what you're thinking about? I mean, that sentence is already kind of a bit of a teaser, right? So
Yes.
What would be kind of the best way to kind of have this kind of, back and forth of feedback between the ML and the physics-based parameterization within
Yes,
the framework?
I was wondering if anyone would call me out on this. So this is literally just thinking, and I don't know. I know Mike's giving a talk later today. I don't think he's here, but so Mike saw my abstention work and thought, well, at least when we do super parameterization, we actually can separate sort of the code out into, does it go to the SP part, or do we go, within the SP, are we using the dynamical part, or could we just go to AI? And he had said that he thought maybe some of the reasons they're having so much trouble getting that ML part to learn is he thinks that there are certain cases that are just so hard to learn that it's confusing a lot of learning on the simple cases. And one could, and it sounds like they're already doing this, set some thresholds or just say, if the temperature is above this and the humidity is below that, use the physics-based version. If not, use the ML. And I would argue that if that is a good idea, maybe abstention or allowing the network itself to tell you when to kick it rather than setting a hard threshold could be a way of saving time when it benefits you, but kicking it to the physics-based model when in real time as the network is figuring out, hey, wait, I don't know this one, I shouldn't even guess, kick it to physics. Does that help a little bit? And I have wondered, with the out of sample climate change, people worry, well, what about cases that we haven't seen before? If you've trained your network properly, perhaps in real time, it can say, ooh, this is not a scenario I've seen before. I'm going to kick it over to the physics where temperature, et cetera, is explicitly considered. This is literally all there is so far, Laura, but just some ideas.
That
So
sounds
we'll
great.
see if
Something
we
we
can
can
fit
talk more
in a last question from Maria. And Abigail, I'm going to ask you to start sharing screen just so that we don't cut into your time.
Hi, Libby. It's Maria. Amazing talk. As a newcomer, this really helped solidify a lot of things that were a bit fuzzy in my head. So thank you so much for that. I wanted to ask you more of a maybe philosophical question. I know we're short on time, but I was curious about your thoughts on those cases that perhaps are too difficult, right, to find predictability. And at what point do we as humans bias our models and thinking about that, right? Like and thinking about this in knowledge discovery, right? So how do we identify where predictability might be coming from for these other cases. And maybe we're just not thinking about that correctly, right? We might be thinking about that ENSO and MJO and you know, this extensive body of literature that exists. But yeah, maybe there's predictability coming from somewhere else and we just don't know yet. So yeah, just your thoughts.
Yeah, so that's the hope ultimately. So the idea here is absolutely the cases that the network says I don't know may not be that it's unpredictable. It could just be we're thinking about it wrong. But I would argue that one could then use this approach to filter out those more predictable patterns that maybe we already know about. And then you could really put your focus in these cases that the network is saying, I don't know, to look for these other states of predictability and that you didn't know were there. And ultimately, for the science in my group, our goal is to identify new sources of predictability. So Maria, you're exactly right. That is something we're trying to do with this method. But I think that's a good ending point, which is just because the network's uncertain doesn't mean there is no physical mechanism of predictability there.
Thank you.
Sorry, Abigail. Okay.
Let's thank Libby for a thought-provoking talk.